MineCycle Material Handling deliver a faster, more competitive bulk material handling design. MineCycle Material Handling is a unique, purpose-built bulk material handling or BMH conceptual design application that provides an automated design environment encompassing civil, structural, and mechanical disciplines. The software enables EPCs and consultants to complete preliminary design up to 30% faster and with higher quality to deliver more competitive feasibility studies and bids. In the demo, the layout is performed in the context of an entire site to enable a clearer understanding of how equipment, conveyor, stockpile, all roads and more function as a system. First, the digital terrain modeling. During the conceptual stage of a project, detailed terrain information may not be available. This is especially true for greenfield projects. There may not yet be accurate survey information or any data collected via electronic remote sensing method. This being the case, MineCycle Material Handling allows a variety of methods to create terrains. Terrain model can be imported, created from Google Earth or Big Maps by simply draping an aerial photograph onto a planar terrain. Or in its simplest form, a terrain model can be created from elements. As more detailed information becomes available, the terrain can be updated. The creation of a DDM is important, as all subsequent design is based around this. There are a range of tools for importing, creating, and manipulating a DDM within MineCycle Material Handling. The process of terrain model creation from Google Earth simply involves locating the area of interest within Google Earth, and then importing that data into MineCycle Material Handling application. This includes any 3D terrain information and a drape aerial view so that existing features can be identified. This data can then be quickly converted into a DTM for use with other MineCycle Material Handling tools. Existing elements can also be used to define the terrain. Contour-based maps may be available, or when working on a brownfield, design legacy data can be quickly converted into a terrain by simply selecting the elements. File can be imported from existing Files can be imported from existing Bentley formats such as GeoPack and Inroads, as well as from a wide range of industry standards including Land XML and TIN. DDM creation is also available from formats produced from electronic remote sensing methods such as LiDAR and from other third-party civil applications. There are a number of options to control the import process. If there is an existing terrain in the file, imported data can be merged within the existing data. Source file unit can be selected to control the scale of the imported terrain. A template can be applied to determine the properties of the created element. Edge processing criteria can be defined. The removal of sliver control, the removal of thin triangles around the boundary. Specifying the maximum triangle length allow external triangles whose external edge is longer in length than the user specified distance are deleted. Source and target coordinate system can be controlled. There is a large library of coordinate system to geographically convert from one system to another during import, and this also can allow correct geographical location of the terrain within the file. The imported data is converted to a DDM element. This can be graphically displayed using a number of predefined display styles to give a better pictorial view of the terrain. Features are maintained from feature-rich data formats. Individual properties can be modified to control the display of the terrain. For example, triangle display may be disabled and contour displayed. Element template can be applied to quickly change the display to user-defined preference. As the terrain is a native element and is referenced into the design file, As new or updated data becomes available, this runs can be easily refreshed within the design. This may be as new data becomes available or a result of civil modification for the terrain from Bentley civil or roading application. The earthworks. The quantity of cut and fill required to establish platforms to support the required storage capacity and to provide sustainable building platform for the necessary plant component is a critical factor in determining the final conceptual design layout. MineCycle Material Handling provide tools to quickly produce site pads and to determine cut and fill volumes. As the site pad can be dynamically modified in relation to the terrain, different options can easily be accepted or dismissed. MineCycle Material Handling earthworks capabilities are in the form of a site pad tools. Those pads can be easily created by simply selecting a point and an orientation. Length, width, and independent values for cut and fill slope can be specified, or the default value accepted. Cut and fill requirements are determined by the elevation of the pad above or below the terrain. Elevation can be specified as an absolute height or as an offset from the terrain. Offset from the terrain is calculated from the intersection point, but a number of options are provided to more accurately define this. Site pad are parametric, so underlying geometry can be easily modified using graphical interactive manipulators. Manipulators are provided to alter the width and length of the site pad to allow movement in the direction of the length or width, a free movement option, and the ability to modify the orientation. Dimensional parametric properties can also be modified to effortlessly update 3D model geometry. Accurate cut and fill calculations are dynamically displayed and are also shown in the site pad properties. This allows analysis of the cut and fill requirement so that the possible option can quickly assessed and either accept or rejected. The ability to create drainage pond from the site pad tool is achieved by simply specifying an elevation which is below the terrain. Here's the pond. Now the stockpiles. Accurate volume and tonnage of stored material is a critical design criterion during the conceptual stage of any bulk material handling project. The ability to dynamically update this data greatly aids this design process. Positioning the location of the stockpile materials in relation to the mine location and transportation facilities need to be quickly and easily manipulated to accept or eliminate each of the different possible scenarios. In MineCycle Material Handling, stockpiles are quickly created by pointing and clicking, and are automatically associated with the existing terrain model. Stockpiles which are created from a single stationary stacking point are as simple to create as selecting a single location point. Accurate volume and tonnage data is immediately available from the tooltip and from the properties dialog of the stockpile element. Materials can be applied to the stockpile element which will affect the tonnage information. A material manager is provided with some predefined material type which can be easily edited or append to as required. Tonnage is not the only aspect of a stockpile affected by a change in the material properties. Factors like repose angle and lump size are considered when calculating the volume of a stockpile. Changing material can apply a different repose angle, therefore modifying the footprint of the stockpile. A relationship to the terrain is always considered. The stockpile dimension may no longer be suited for the underlying terrain or construct pad. A linear stockpile that can be created by a rail mountain stacker or an aerial tripper stacker is quickly defined by simply specifying a start point and an end point. Height is also required, but a default can be used as it can be subsequently edited. All type of stockpile are parametric, so underlying geometry can easily be modified using graphical interactive manipulators. Dimensional parametric properties can also be modified to effortlessly update the 3D model geometry. Notice there is a dimensional parameter allowing modification of the width on the top of the stockpile. This allows the definition of stockpile generated by slewing stacker or for simulating stockpile with push-out capacity. Radial stockpile created from radial or slewing stacker are also easily placed and modified. Additional parametric parameters are provided to allow adjustment of the slewing radius. Parametric conveyors. MineCycle Material Handling provides rule-based conveyor layout tools to govern design parameters including vertical curve, incline constraint, material trajectory, true angles, burn-in height, tonnage, and more. These design parameters are considered dynamically during layout of the conveyor path, enabling the designer to make refinement. This intelligent layout saves significant time by eliminating the guesswork and iteration found in traditional conceptual design workflows. Consistent with the previous discussed tool, conveyors are also placed by simply specifying the tail point and the head point of the conveyor. The ability to relate the conveyor to DDM and initial offset from DDM allows the rapid placement of conveyor. Conveyor tool provides a number of parameters allowing specification of large range of conveyor design. All MineCycle Material Handling components allow specification of tag properties including name and description. Conveyor properties provide initial design criteria as a design capacity tonnage specified, and if a material is assigned, calculated information becomes available. Burden height and maximum and minimum incline angles. Once the conveyor is placed, all horizontal and vertical height are also calculated. Conveyor can also be modified using graphical interactive manipulators. Initially, head and tail points can be modified, but if a profile view is displayed, elevation can be adjusted and new control point can be inserted. This allows control of additional properties of the conveyor, including the incline and decline angles. Optimization of ground travel can be performed to minimize the amount of costly elevated travel. As the conveyors are rule-based, parameters like minimum radius can easily be identified and rectified. Additionally, visual interference checking can be performed. A profile view allows optimization of the belt properties. Change to material, belt width and speed can very quickly be visually analyzed to check the primary design is going to function as intended. Material trajectory calculations are also dynamically being adjusted as calculations are processed using each of the design parameters. Head and tail design can be selected from multiple configurations, and take-ups can also be specified from multiple configurations. Although MineCycle Material Handling provides an accurate conceptual conveyor design, this can be checked by interfacing with conveyor analysis solutions. Data is first updated in the consensus model. Then an application-specific data file is created. The created data is imported into a dedicated conveyor design application. In this situation, the dedicated conveyor design application is Sidewinder. The material data, build data, and also information relating to the head and tail configuration selected are shown here as pulley and motor information. A profile of the conveyor is also displayed. Calculations are conducted against the existing design and performance is checked. Sidewinder highlights some areas of concern. The belt width is incorrectly sized and the radius is too large for the capacity of the belt. Modifications to the design are made here until there are no more warning. The change data is exported back via data file. Once it's done, we can export back. The modifications are updated into the consensus model, and the differencing interface allows the acceptance of or rejection of important change. All the changes are listed and then can be accept or reject. The consensus model interface provides data synchronization, change management, and a revision history. So that design can be visually correct for presentation purpose, conveyor cover, gantry, and walkway properties can be adjusted to give a more realistic representation of the conveyor. Conveyors can be linked to one another. This allows accurate location of the intersection point, or IP, even if the conveyor don't physically intersect. These relationships are maintained even when the conveyors are moved or modified. Now the parametric equipment. MineCycle Material Handling includes parametric design tools for all transfer equipment type such as screening, crushing, and transfer stations. This allows equipment to be easily placed and then quickly modified using head-up editing tools. Modification of equipment parameter triggers the software to automatically adjust the connected conveyor to reflect the change. MineCycle Material Handling provides a range of parametric equipment. Enclosed and open buildings, round and square bins, and a bin with double hoppers. 3 styles of crushers: cone, jaw crusher, and gyratory crusher. And a screener. Although styles, the equipment is detailed enough to provide accurate representation for conceptual presentation purpose. All parametric equipment follows the same placement process as tool previously discussed. A crusher can be placed by selecting a position on the terrain and then by specifying an orientation. They are by default associated to the terrain and may be freestanding or associated with a conveyor. All parametric equipment have a number of IP points to allow connection of the ends of a conveyor. Once linked to a conveyor, any change to equipment location allows the conveyor to update. This allows the free exploration of different design scenarios by moving or rotating sections of plant without losing an important relationship between equipment and conveyors, and all still interacting within the constraint of the terrain. Each piece of parametric equipment has a range of properties to correctly represent it within the design, and any change of these properties are reflected by update in the conveyor system. As the parametric equipment is displayed as an open structure, if necessary a building can be placed to clad the structure. Or freestanding building can be used to populate the site to represent other required structures. A number of structural components are available to give more realism to the conceptual model. Take-up towers can be added in vertical or horizontal configurations. They are simply placed at the location of the take-up along the conveyor. Also, trestles can be parametrically placed as support for the conveyors. Different pieces of equipment can also be added to the design. Trucks, trains, reclaimers, and stackers are provided as samples. These are also placed relative to the terrain. Now the presentation. MineCycle Material Handling provides the benefits of an intelligent 3D model without the typical complexity of a 3D CAD. Designer can use traditional 2D plans and profile workflows and let the software create the 3D model, arrange the 3D equipment models over the terrain, and let the software create standard 2D views. The 3D model updates production of high-quality 2D drawing, enables the creation of stunning planned fly-through and photorealistic 3D renderings directly from the design environment, and provides a ready-to-detail model. This promotes more compelling, easy-to-understand proposal and saves time communicating with stakeholders, generating documentation, and transitioning to Phase 3 and 4. The print preparation. Integrated print preparation tool can be used to facilitate construction plans. The print preparation capabilities include border placement, legend creation, detailed view representation, and many more features. Construction nodes can be added, and the layout information can be scaled as appropriate. Print preparation functionality is delivered with simple border templates and other items. This facilitates quick startup, but print preparation is also fully customizable to meet organization standards. The rendering and animation. Industry-leading tools produce like-life visualization of model using the Luxology rendering engine, supporting point and shot, physically correct materials, and lighting libraries, and rich photorealistic content. Animation capability produce realistic movies and simulation from design and operation model. Die model support. Effective and efficient sharing and distribution of information is critical to the success of every BMH project, and when done well, this can reduce errors, compress the project schedule, and reduce project cost. Sharing and distributing information across a distributed project enterprise is difficult given the diverse data sources and formats that are required to complete a project. iModel and the supporting tools and technology were created to facilitate the sharing and distribution of information regardless of the source and format of the information, enabling users to provide the information mobility required by the project. Thanks for listening.